When we think of a computer today, we usually imagine something silent and invisible, billions of transistors carved into a sliver of silicon, no larger than a fingernail. But in the middle of the 20th century, computing was a physical, mechanical, and loud experience. Before the microchip, logic wasn't something that happened in a vacuum of stillness. It was performed by moving metal and glowing glass. If you were to stand inside a computer room in 1945, you wouldn't hear the hum of a cooling fan. Instead, you would hear the rhythmic clicking of thousands of metal switches, sounding like a room full of energetic typewriters working in perfect synchronization. The first building block of these massive machines was the electromagnetic relay. At its heart, a relay is a simple device that uses a magnet to flip the switch. It consists of a coil of copper wire wrapped around an iron core. When an electric current flows through that coil, it creates a magnetic field. This field pulls on a small hinged piece of metal, called an armature, snapping it down to touch a contact point. This physical movement completes a second circuit. When the power to the coil is cut, the magnetism disappears and a tiny spring pulls the metal arm back to its original position, breaking the connection. This simple on or off state is the foundation of binary logic. By connecting these relays together in specific patterns, engineers could create logic gates. For example, if you wire two relays in a row, the current only flows through the second one if both magnets are energized. This is an AND gate. If you wire them side by side, current flows if either one is activated, creating an OR gate. Using these physical movements, early computers like the Harvard Mark I could perform complex calculations, but they were limited by the laws of physics. Each calculation required a physical piece of metal to move through space, which took time. The relay was reliable, but it had a speed limit. No matter how much power you apply, you could only move a metal arm so fast. A relay could flip, perhaps 50 times a second. For the mathematicians of the 1940s, this wasn't fast enough to solve the complex ballistic equations required during the war. They needed a way to switch electricity without moving any physical parts at all. This led them to revisit a discovery from the world of radio and light bulbs, the vacuum tube. These glass cylinders would become the first step toward the electronic age, replacing mechanical inertia with the speed of electrons. To understand the vacuum tube, we have to look at a phenomenon called thermionic emission. Inside the glass bulb, most of the air has been removed to create a vacuum. There is a metal filament, much like the one in an old incandescent light bulb. When we run a current through this filament, it glows orange and becomes incredibly hot. At this temperature, the atoms in the metal become so agitated that they actually start to boil off electrons. These electrons form a tiny cloud around the filament, waiting for somewhere to go. This is the source of our signal, known as the cathode. Across from this hot cathode sits a cold metal plate called the anode. By applying a positive voltage to the anode, we can attract those boiled off electrons. Because electrons are negatively charged, they jump across the empty space of the vacuum, creating a steady flow of electricity in one direction. This basic two-element tube is called a diode. It allows current to flow one way, but not the other. It was a useful device, but it wasn't yet a computer component. To make it act like a switch, engineers added a third element, a tiny wire mesh called the control grid. The control grid sits directly between the hot cathode and the positive plate. By applying a small negative charge to this grid, we can repel the electrons trying to fly past it. It acts like a gatekeeper. A small change in voltage on the grid can completely stop the flow of millions of electrons or let them through instantly. This is the triode. Because there are no moving parts, only the motion of electrons, a vacuum tube can switch on and off millions of times per second. This was thousands of times faster than any mechanical relay, and it changed everything. However, using vacuum tubes at scale presented a new set of problems. The ENIAC, one of the first truly electronic general-purpose computers, used nearly 18,000 of these tubes. Because each tube functioned essentially like a small heater, the machine generated an immense amount of thermal energy. The room housing the ENIAC reached temperatures of over 120 degrees Fahrenheit. The power required to keep those 18,000 filaments glowing was staggering. The computer consumed 150 kilowatts of electricity, enough to power a small neighborhood. The brain was now electronic, but it was also a furnace. Reliability was another constant battle. Like light bulbs, vacuum tubes eventually burn out. With 18,000 tubes in a single machine, the statistical probability of one failing was extremely high. In its early days, the ENIAC suffered a tube failure nearly every few days and sometimes every few hours. Engineers had to develop specialized testing routines to find the dead tube among the thousands. This is also where the term bug became literal. In the era of relays and tubes, the heat and light often attracted moths and other insects into the machinery, where they would get stuck in the contacts and cause a short circuit. Despite these challenges, the vacuum tube era proved that binary logic could be processed at incredible speeds. It allowed for the first complex simulations of weather, atomic physics, and mathematical constants. But engineers knew they couldn't keep making computers larger and hotter. The glass was too fragile, the heat was too intense, and the scale was too cumbersome. They needed a solid material that could do the same job as the vacuum tube, controlling the flow of electrons without the need for a vacuum or a heated filament. This search would eventually lead to the invention of the transistor. The transition from relays to tubes and eventually to silicon is a story of removing the physical friction from thought. We went from moving metal arms to moving clouds of electrons in a vacuum to moving electrons through solid crystals. Each step made the computer smaller, faster, and more efficient. Yet, the fundamental logic remains the same. The N OR gates that we built out of magnets and light bulbs in the 1940s are the exact same logical structures that power the smartphone in your pocket today. When we look back at these mechanical monsters, we shouldn't see them as primitive. They were a brilliant solution to a fundamental problem: how to make a machine think. They remind us that computing was once something you could touch, hear, and feel the heat from. It was a craft of glass and wire. The next time you use a computer, remember that beneath the sleek glass screen, there is a long lineage of clicking magnets and glowing tubes that first taught us how to turn electricity into information.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.